So here we have a graph of the path of a particle's motion over time. We can see that it's moving up and then down and then up and then down. And so it turns out that we can use this sort of wave to figure out the period of a particle as it moves up and down, right? Because the x-axis is time, the distance between two crests will be the time that it takes for a single particle to move all the way down and then all the way back. And that's our definition of period. So because the x-axis is used to measure time, we can measure a distance on the x-axis to figure out a time in seconds, which will be the period of the wave. And of course the frequency, we can just use this equation to find, f equals 1 on t. So what this will give you is how many wavelengths pass through 1 second. So if we have a time interval of 1 second over here, then the frequency will be the number of total wavelengths in that interval. Make sense? Our fixed point is the point at which we're measuring the wave. So the number of wavelengths that we get in 1 second shows how frequently the crests of the wave are passing through that point. If we know its speed, then we can find its wavelength. And if we know its wavelength, we can find its speed, simply with this equation, v equals f lambda. Calculate this wave's frequency. Now what we're given here is a graph of displacement over time. And that means that we're able to measure frequency and period just by measuring properties of this graph. So we can see that there's a 1 second over here, and the frequency of a wave is how many wavefronts pass through a particular point over 1 second. So if we were to measure the number of wavelengths in 1 second, we'd be able to find the frequency of the wave. We can see that there's 1, 2, and a half wavelengths altogether, right? So this is one whole wavelength, this is a second whole wavelength, and this bit at the end is only half a wavelength. So our answer is that the frequency is 2.5 Hertz. We could also figure this out by measuring the period of the wave. That's how long this interval is of one wavelength, and then taking 1 and dividing it by that wavelength. We will of course get the same answer of 2.5 Hertz. And that brings me to the next question. What is the period? Now it turns out, because we already have the frequency, we can calculate the period just by taking 1 and dividing it by the frequency. So doing that, we take 1 over 2.5 equals 0.4 seconds. So that means that this point on the graph over here is 0.4 seconds, and after a second wavelength we'll be up to 0.8. After half a wavelength, it'll only take half this time, so we'll only be adding 0.2, which brings us all the way up to 1, exactly what we see on the graph. Find the amplitude. Now remember, the amplitude is the displacement of a particle in the wave away from the rest position. The rest position is this 0 on the y-axis, and so we can see that our amplitude will be, that's right, 0.4 centimeters. Finally, find the velocity, given that its wavelength is 50 centimeters. So that means that if we were to look at the wave as a whole, and as it traveled, then the distance between two successive crests would be 50 centimeters. So how do we find the velocity of the wave? Well, we know that it travels one wavelength in 0.4 seconds. We know that one wavelength is 50 centimeters long. So our speed is 50 centimeters over 0.4 seconds. Of course, the other way we can do this is, instead of taking distance over time, we can simply say distance times frequency, because frequency is 1 over time. So we use our equation, v equals f lambda, we put in f 2.5 and lambda 0.5 meters, and we end up with 1.25 meters per second as the speed of the wave.